Okay, let's begin the later session of this lecture. First, I found one typo in the previous lecture slide. This is a previous slide. So we are somewhere here. We start in the middle of this and go back one page. This was wrong. Okay, this was typo. VAP divided by D is here. Okay, if you want to move this one to there, then you can remove this by this. Okay, maybe that was your question. Okay, right. But this is a correct one. That I had one typo there. Okay, so now we have. Oh boy, this one correct here. Previous one was wrong. Okay, there are some small typo mistake, and when I referring some variable, I'm talking something else, referring to something else like that. Okay, but please understand that you can catch some minor mistake. Okay, I hope so. Okay, and I make some mistake, some grammar mistake too. Okay, but that is the limitation of using the foreign language. All right. Okay, so we are in the middle of this, and this transfer function is important. If the AC noise coming in to this buck converter, that will be attenuated by this power stage, and the magnitude of the ripple will be reduced. So this represents noise transmission characteristics of converter. And the other transfer function is this one, D. D controls this dependent voltage source and dependent current source. And transfer function from these two things to there is due ratio to output transfer function. This is very important. Your control will be designed on this, based on these characteristics. So this forms the fundamentals to design the control circuit of your converter. So this is very important. And another one is load current to output transfer function. It represents if there are some AC disturbance, then how large the disturbance in the output voltage. You want this thing to be zero or as small as possible. For the ideal voltage source, regardless of any presence of this perturbation, this output voltage is fixed. There is no ripple component. So this represents the goodness, the performance, goodness as a voltage source. So these three transfer functions are important. And for converter case, so you replace this PWM switch, including this resonant, this inductor, something like this, and pin-to-pin replacement of this functional block to the PWM switch is just a small signal model of PWM switch, and everything will be changed to this small signal variable and S-domain variable. So I need to use 2 SL and 1 over SC here, okay, but this one remains the same. So this is the small signal model of a converter. Okay, it is derived through the averaging and the linearization. Those skips are not shown here, and we'll go back to the derivation of these things. But understanding this is enough for now. Using this, we explore the frequency response characteristic of this converter. So this is the power stage model of converter, small signal model of converter. If you take a look at this part is, it becomes the small signal source, disturbance source. It represents disturbance in the input voltage or disturbance in the continuous due ratio, but output voltage disturbance is located here. But this, basically, this part is disturbance source. How about this part? This part has a name. What is this? This is low pass filter. All right? So it has some disturbance source and low pass filter, and they are connected through this 1 to D ideal transformer. So you expect the transfer function of this thing is very similar to the low pass filter, which is true. Okay? So I said you have 3 transfer functions of interest. One is from here to there. The other one is from here to there. And another one is from here to this, our voltage. Okay? So let's consider this. Let's consider this. This one. Okay? So you want to evaluate the transfer function from here to the our voltage with this is 0. Okay? This is linear system. We are talking about superposition. So for that, this is connected. Okay? This is connected. Right? And this is active. This is active. And this should be killed. So this is open. This is the open. Okay? The current source is opened to remove this functionality. Then this is shorted. The ILD is coming here. Then that current will circulate. There is no reason to go to this direction. This is shorted. So this IL part is just circulating this. Means this part is nothing to do with transfer function. Okay? Because this is only circulating this primary side of ideal transformer. So this is nothing. It's not affecting anything. And this is shorted. Then this VSD. Okay? Then D is cancelled with D because 1 to D ideal transformer. So VS is coming here. And VS is appeared here by this voltage division. That is shown here. Okay, so this is VS. So this gain is VS, obvious. And this is second order function because this is for second order low pass filter. And as I said previously, if RC is connected with the series, this RC connection, in series connection, will produce 0 at that particular frequency. I'm not talking about the sinusoidal frequency. This some frequency, this becomes 0. Means output is 0, that becomes 0. So we have ESR 0 in the numerator, and this the second order quadratic function in the denominator, and the constant gain is coming here. Okay? So in that manner, you can derive all the transfer functions, okay, easily. And this omega ESR is given by this, and omega naught is the exact one. But with this assumption, this is parasitic resistance of capacitor, and that of inductor that will be very small compared to this R. So this is is well satisfied. Then this is simplified to this, and this is simplified to this. But you don't want any approximation, you can use this, but that is not desired. Okay? That is unnecessary. All right? And this one, think about this. This is the transfer function from load current to our voltage. Okay? And this one becomes 0. D is 0, so opened. And D is 0, shorted. This one is 0, shorted. Okay? So primary side of this ideal transformer is shorted. That means secondary side is also shorted. That is the characteristic of ideal transformer. Then the remaining thing is this one. This is inductor, not capacitor. Oh, I'm sorry. Okay. Oh boy. Inductor ESR and capacitor ESR and R, node resistor, and this is GP. GP is output impedance R. Okay, that is the parallel combination of 3 things. Okay, because of the presence of the L and C, this is the second order one. So this denominator is commonly appears here at very low frequencies. This is open. This is shorted. Then the remaining one is RL, because RL is very small compared with this. So at low frequency, what you are seeing is just RL okay, this branch becomes infinity impedance, all right? And as I said, there is 1, 0 here. This is ESR 0. And also this branch has 0 because you calculate the impedance of this. And then at this frequency, this occurs at low frequency because RL is very small compared to the L. Okay, so this is the second order transfer function, same denominator. This is a low frequency value, but it has 2 zeros. This ESR 0 is common in 3 transfer functions, but this additional 0 is coming here because of this. Okay, 1, 0, 2, 0, and 0 frequencies like this. Okay. If you understand the pole and zeros, you can write down this immediately. Okay, otherwise you do some circuit manipulation, then you will have the same result. Okay. Okay. So transfer function of this, you derived transfer functions of 3 important quantities. This is the GVD, magnetic curve, and GBS, magnetic curve, and the output impedance GP, magnetic curve. So this is the, let me explain this. We know, right? This is, you have this expression, okay? So from this low frequency gain is D, actually this is what? This is DC gain of buck converter, okay? In CCM, DC gain of buck converter is D, so this should be DC gain. Because at low frequencies, you goes into this direction forever, you will come up with the DC, and DC remains constant, okay, all the way, right? So this is the DC gain of the converter. And expression for this is from this one. This is asymptotic plot. So this omega naught is double pole frequency, and this is, there is a 0 omega ESR. We are assuming this comes earlier, much earlier than this one, which is true for the most practical case. So based on this assumption, this omega G, this 0 occurring at output impedance is very small, and omega naught is in the middle, and we are assuming this omega ESR is very large at higher frequency. Then you have this kind of asymptotic plot, and this is the expression for the corner frequency, pole frequency, and double pole frequency, and the 0 frequency. And this is what? Quality factor. So you can predict this, right? So this is the result of 3 asymptotic plot of 3 transfer functions of Buck power stage, and maybe this is the correction to have accurate curve like this. Okay, this is also easy. And let me explain this one, this curve. Okay, implication of this transfer function is more important than derivation or sketching of this. Okay, suppose this is the input to output transfer function of some buck converter, and the buck converter is shown here. Input voltage, DC voltage is Vs, and we have some AC component on the top of this. So this is it. Okay, DC value, average value is 16, and we have some AC component on the top of this, and the switch drive signal D is 0.25, and this is periodic. Okay, assume this is periodic. So this is periodic. This means Dewey ratio is fixed. Okay, this is D is also this continuous Dewey ratio. We went through this, right? This time averaging while sliding this integration window becomes constant when this is periodic. So this is the input voltage and this is out voltage. Okay. This is easy to understand and reasonable because the input voltage has some AC component, sinusoidal ripple, that out voltage will be sinusoidal and it has some ripple component. Okay. How about the magnitude? Then you need to take a look at this. This is input to output transfer function, Bode plot of that. So maybe you consider this frequency. This is 1 kilohertz, 2 kilohertz, okay? And this AC component is this one. So VST is actually 16 plus 0.1 plus sine 2 pi 2 kilohertz. I generate this signal using this function, okay? Then you need to take a look at this frequency. At this frequency is this one. So at this frequency, the magnitude is minus 20 dB, which is 0.1. Okay. Phase is, assume this is minus 130 degree. Okay. Or something else, but consider this. Okay. Then what is the output voltage? The DC output voltage will generate, DC input voltage will generate output voltage regardless of this curve. So you have this. This is the input DC voltage, and that is the steady state Uri ratio. So with this, you have this, okay, 4. But this sinusoidal waveform, you need to take a look at this. Okay, this is 2 kilohertz, and magnitude is reduced by 1/10. Okay, and phase delay is this one. Then the prediction is this one. This 0.5. So magnitude of this is 0.5. Then peak to peak is 0.5 times 2 is 1 volt. Okay. Then this is the sinusoidal waveform, but you should multiply this by 0.1, this one. Okay, then we'll give you this one. And there is additional phase based on this. Okay, so you have this phase. Then output is this one is coming from these DC, 2 DC components, and this one is coming from this and this AC component, and composite signal is this one, and you have some ripple component which is ignored in this simplified analysis. So this is our prediction, and simulation result is shown here. So just average of this, just line, continuous line passing through the middle point, and this should be this one, 0.05 times 2, peak to peak is 0.1 volt, which is very accurate. And if you take a look at closely at this point, there is a phase delay. The phase of this one is 0, but phase of this one is not 0. Probably this phase is minus 130 degree. Okay? So this is the implication of frequency response of PWM converter. Right? Knowing this is very important. If you have some interest in at this some other frequencies, maybe 10 kilohertz, then you need to take a look at these 2 points. Right? If you have interest in at this resonant frequency, take a look at this and these phases. Right? So that is, this interpretation is same as the case of linear time invariant system. We went through this, okay? Exactly same analogy applies here. The assumption is variation of input voltage is relatively smaller than DC value of this. This is 1/16, right? 1/16 is more than enough. And another example, this is the same converter, but now we consider this dual ratio to output transfer function. So now this is fixed, 16 volt. So I'm not showing this 16 constant, but this is constant, and this is changing. Now this duty ratio is modulated to generate this kind of waveform. It's very easy to generate this using some simple program. Then maybe this duty ratio is large, duty ratio is very small, large, small, something like that. Okay, so perturbation is this. Okay, duty ratio is changing this at this high frequency compared to the previous one. So the frequency of this modulation, sinusoidal modulation, I select this frequency 5 kilohertz, because at 5 kilohertz it passes the 0 dB line. That means is unattenuated. This ripple AC component is deflected without any change. Because of this, but phase will be delayed by, for example, you can be accurate if you want by taking a look at this using some software, but assume this is true. Then duty ratio is, this is the DC value of DT, continuous duty ratio, and we have this sinusoidal component at this frequency, and this DC is this one, 0.25, so same out voltage will be generated as the previous case, okay? But due to this ripple component in duty ratio, we have this is 1, okay, which is 0 dB, this is 1. So we have 4 DC component and this sinusoidal component. So this is 0.05 times 2 is 0.1. Same thing, okay? This is 0.01. Okay, so you can confirm this. This validate the correctness of our small signal model for this kind of perturbation. If this AC component becomes this one, then everything will screw up. Okay, now this is okay, right? So implication of frequency response of PWM converters are very similar to the almost identical to the time invariant system. That is, in the time invariant system, if you know the frequency response, you know all the property, steady state property and dynamic property of the linear time invariant system. Same is true here. Okay? If you know this, maybe some step change response and all the dynamics are apparent from this analysis if the disturbance is sufficiently small. Okay? Operating point does not deviate much. Then you can consider this one is linear time invariant system. And you can use the same technique for the linear time invariant system, which is a very nice thing to do. Okay. All right. So this is evaluation of access of the accuracy of frequency domain analysis. There are 3 curves. Actually, there are 3 curves superimposed. One is small signal simulation, means the analytical calculation of small signal model, transfer function derived. Small signal derived transfer function. Okay, maybe you put some software, blind software will generate this. Okay, MATLAB or something, and another one is experimental measurement. Okay, it is the same except this high frequency noise. High frequency noise is here, and another one is computational method. We discussed this before. Okay, without using small signal model, without any experimental things, hardware things, we assume the time domain. We perform time domain simulation, and from the time domain simulation, we extract the small signal transfer function in the same way as the that of impedance analyzer. That result is here. Okay, so that at this frequency they are the same, and this frequency there are some deviation. This is because the noise at high frequencies, the signal level is very small here, very small, and the noise is start talking. Okay, then noise is influential in measurement, in simulation. Numerical noise is generated. That will be some case amplified, will produce this kind of spike. You just ignore this, okay? That's, and another reason ignoring this high frequency is the validity of this older modeling process is, it is valid below the Nyquist frequency. Nyquist frequency is Hepter switching frequency. Okay, below that is only valid, the aliasing effect, okay, in communication they are talking about a lot, okay. Because of that, we are controlling this duty ratio only once in one switching period. That is a sampled data system in exact sense. Because of that, at this frequency, everything breaks down, and you don't trust this, okay. Maybe experiment is okay, but other than that, experiment is also you need a good equipment to accurately measure high frequency characteristics. But usually, the crossover frequency of this thing is way below this one. So fortunately, you don't have to worry about this. Okay? So this is about the frequency response of power stage. Okay, starting from next lecture, we'll be talking about something else. Closed loop performance of PWM converter. Previously, we were talking about only power stages. Now we are talking about the closed loop performance. Closed loop means there is a feedback. Performance means performance as a voltage source. That is very important. Okay? PWM converter, eventually, it should be good voltage source. All right? So, okay, we'll stop here. Okay, and remember the midterm things. Okay, all right. Okay, thank you for your attention.